So this is like starting in the middle of pipelining, because the assumption is that you have understood what is pipelining, how is pipelining done, what are structural hazards, what are data hazards, what are control hazards. And I am talking about how do you improve stalls in control hazards. Okay, so this is the, like I said, the second half of the control hazards video of Bhaskar and Raman, and followed by other topics which are not covered in the videos. So I do see that some people have not seen the videos, and I don't know if others have understood everything. If you don't ask questions, and then there is nothing I can do. I assume that you understood everything, and I am going to proceed. In fact, I put the delayed branch because I was not sure how many would have understood it. That's all. Otherwise, I don't have to talk about that also.
Ma'am,
Yeah.
I was seeing this control hazard video, ma'am. That
Mm.
the first question, where you have asked how many stalls will it take, like should we put after the branch, like instruction, so that there won't be any control hazard.
No, that doesn't
Uh,
seem like a correct question.
1 second.
If there are stalls, then there is a hazard, right? I mean, if there are stalls, means there is a hazard. Otherwise, there is no stall at all.
In that question, the
Yeah,
answer
I'm
for that.
logging into the Moodle server.
In practice.
Hmm?
How many stall cycles will be needed before the next instruction is fetched?
Mm.
Like normally, after the execution cycle of the branch, we'll know that whether branch is going to the next, which instruction the branch is going to.
Yeah, so if a branch completes at the end of 5 clock cycles, how many stall cycles will be needed before the next instruction is fetched?
Yes.
Okay. So you have to draw the line. I mean, sorry, what I mean is you have to draw the pipeline and see what happens, right?
Yes, ma'am. Right.
So if you have branch instruction, you have a IF, and then you assume that EX itself, you need another 3 cycles before the condition and the target address are determined. So until you get the condition and target address, you don't know whether you're going to fetch the next instruction or the target instruction. So that many stalls you'll now have to introduce. So when branch instruction D, then itself if you don't know, right? So you stall from
Yes,
there
ma'am.
onwards until the end of branch instruction.
Yes,
So it should be
like
4 cycles that we put.
according to the video,
Mm.
the video he just stalls it until the execution is done.
Yeah. In the video, he has the branch completing in the 3rd cycle. No, because I put this question before the techniques to reduce stalls and control hazards. So one of the techniques the book talks about, and which therefore Bhaskar and Raman talks about, is trying to finish the branch in the second stage itself, which is basically in the ID stage, the decode stage, you also finish evaluating the branch condition as well as calculating the target instruction address, so that you at the most have one stall if no other optimizations are used. But the question I have given says that branch instruction completes only at the end of 5 clock cycles. Okay.
Understood. Yes.
Branch instructions, in fact, take long cycles. It's not, MIPS is a very, very, what I say, simple processor. So it finishes the branch condition checking as well as target instruction address calculation in the ID stage. But most real-time processors don't do that.
Okay.
So you'll end up having to wait that long before you can execute the next instruction. So control hazards are a big problem in pipelines because they reduce the throughput significantly. Any other questions? So people understood branch not taken optimization. Basically assume that branch is not taken. Okay. So when in fact, the way the Georgia Tech person explains that is very interesting in some sense. So the point is that when you fetch an instruction, you don't know whether it's a branch instruction or not a branch instruction. So if you do not assume that branch is not taken, even if the instruction is not a branch, you can't get the next instruction. Why? Because you don't know whether the currently fetched instruction is a branch or not until you decode it. After decoding only, you know whether it's a branch. Then if it's not a branch, you'll fetch the next instruction. So there will be one stall cycle always if you do not assume branch not taken as your prediction. So when you make the assumption that branch is not taken, you fetch an instruction. In the next cycle, you fetch the next instruction, sequential instruction, without worrying about whether the previous instruction was a branch or not. So when branch is not taken, then anyway you have to fetch the sequential instruction. So, it works very well, generally speaking, for most of the code, and reduces the stall cycles quite significantly. That's the intention of assume branch not taken. So this is the delayed branch, what is called as the branch delay slot. So in the MIPS pipeline, like we said, there is only one stall cycle actually, because if in the ID, in the decode stage, it is able to finish everything, both condition checking as well as the determination of the branch target address. Then if your branch is taken, that particular instruction, maybe you would have fetched the sequentially next instruction. So that instruction should be converted into a no-op, which is essentially like a stall, right? So therefore, there is only one slot, which is basically that is going to be a stall slot. And the per point of delayed branches, I mean, this particular slot is called as the branch delay slot. How do you make sure that this slot is utilized, effectively, so that you don't actually have to convert that instruction fetched into a no-op? That is the main idea behind delayed branch. So there are three possibilities. The first possibility is that a code, an instruction which is there before the branch, if you can move it into the, basically the delay slot, then you don't waste anything, because this has to be executed whether or not the branch is taken. So by doing this, we are effectively utilizing this slot and having no stall, because by the time this instruction is fetched and decoded, branch would have known whether it is going to be taken, not taken, and so the next instruction which is fetched will be the right instruction. So it will be the next sequentially instruction after the branch if it's not taken, and the target address if it is taken. So that is the point here. But in all conditions, it may not be possible to move this. When is it not possible? Supposing you do a DAD here and then say if R1 equal to 0. Normally, that's what we do. We calculate some value and then say whether that value satisfies some condition. In which case, there is a dependency, right? There is a dependency of the branch on the previous instruction. So the previous instruction can't be moved after the branch. That is one of the problems. So in that case, you may be able to do something like this. So you have a loop here. If R1 equal to 0, you go back to some instruction. So here, what are you doing? You're repeating that instruction in the branch delay slot. You're repeating that instruction in the branch delay slot, and when you go back in the loop, you go to the instruction just after D sub. By doing this, we are actually utilizing the branch delay slot effectively. But this is only true if the branch is taken. If the branch is not taken, then this instruction obviously is wasted. Same thing happens here, where we are basically saying that whatever is the instruction that is after the branch, when the branch is not taken, is moved into the delay slot. But again, if the branch is taken here, then we have a problem, right? So if the best is this, which ensures that the slot is effectively used with no instruction wasted, right? No instruction which is fetched is turned into a no-op. So that's the best thing we can do. Of course, the delay slots will be much higher in many processors, but usually they only use delayed branch mechanism when there is only one stall slot for the branch, because it's very difficult to bring multiple instructions into delay slots. So this method is only used if there is a single delay slot for the branch, not in other conditions where like my question, where I say the branch takes 5 clock cycles to finish, then you will actually have 3 delay slots. That would not be easy to handle with delayed branches. So that's not the technique which we'll be using. Okay. So that's about delayed branches. Any questions?
Ma'am, here for this branching, like be- so in the first case we have taken the instruction before the branch and putting it in the delay slot, right, ma'am?
You're right.
Why can't we do that for the other two also?
No, the thing is that in all, if you can find such an instruction which you can move in after the branch, it is very nice. But under all circumstances, we may not find such instructions because we may find that all instructions depend on each other before the branch. And the branch instruction depends on the previous instruction, some instruction, right? Then
Yes, ma'am.
you can't, like I said, if you say D add R1, R2, R3, and then instead of saying if R2 equal to 0, this had been if R1 equal to 0, then until you calculate R1, you cannot take the branch. You cannot move DAD into the delay
Yes, ma'am.
slot because the decision of branch is based on the output of DAD.
Yes, ma'am.
So when
Yes,
you
ma'am.
have such situations where the all the instructions are dependent on each other and the outputs of those instructions are needed to determine the branch, then you can't actually move the instruction after the branch. That is the problem. As long as you can find such an instruction, that is the mechanism the compiler will choose because this is done by the compiler.
Yes, ma'am. Yes.
Okay, so um, basically, therefore, what they do, they go for what is called as branch prediction. We are going to cover two of them today, but actually, in the next chapter, there will be more complex predictors. I thought about it. Should I do the all predictors together or not? Finally, I decided let me go with the chapter chronology so that you also can read the textbook chapter wise rather than search where the other material is. So Bhaskaran Raman hardly talked about this. He just said, oh, he did talk a little about the 1-bit predictor, but nothing at all about the 2-bit predictor. And he didn't talk about how they help. And so the intention here is to introduce this, but later I'll put up the Georgia Tech videos. But only thing is in those videos, you need to see the videos only up to a point. Beyond that, it gets very complex actually. They talk about very complex branch predictors which are not covered in the book also. So we don't need to go there. But 1-bit, 2-bit, and other things, he has done a very good job. So I want you to go through those videos later. So this 1-bit predictor is also called as a branch history table, right? So what does it contain? It's a table which consists of zeros and ones, where um, 0 means that the branch is not taken, and 1 means that the branch is taken. And the the table is indexed using the branch address. Now I'm going to also, okay, let me just do a few quick clarifications from Bhaskaran Raman's videos. Bhaskaran Raman says that write after write hazards and write after read hazards are not possible in the MIPS pipeline. Be very, very clear about it. He keeps saying it's not possible in the classical 5-stage MIPS pipeline. You have to be very clear about that because we will be covering, or I'm intending to cover, what is called as the floating point pipeline of MIPS. where we will encounter right after right hazards. So you shouldn't get confused. Bhaskar Raman said there are no right after right hazards, and ma'am is saying there are right after right hazards. If you have a 5-stage pipeline, then you do not have right after right hazards. But it's like we keep going from simple models to more and more complex models. So, in fact, when we start looking at instruction level parallelism, we'll see that we do a lot of out of order instruction execution. So, you will write the program in a certain order. Your compiler itself will rearrange the code so that you have a much better mechanism of executing it without stalls, right? It's called scheduling, and the compiler does a lot of scheduling of instructions. We'll see that also, how, some examples of how compiler schedules the instructions so that there are no stalls. But then we are also going to read algorithms which actually execute instructions out of order. You try to fetch some instruction or data for an instruction, and that's not in the cache, or maybe not even in the memory. Then you proceed further. Please remember what we said is a non-blocking cache, hit under miss and even miss under miss, right? So you are able to proceed to the next instruction even though the previous instruction resulted in a miss in the cache. This will mean that instructions are executed out of order. When you do that, you are going to see right after right hazards as well as right after read hazards. So we have to take care of all of them when we talk about those algorithms in the next chapter. So don't assume that there are no right after right and right after read as hazards in MIPS. They do occur, but not if it is an in-order 5-stage processor. Okay, that's one clarification I wanted to give, because I don't want you to carry in your mind, oh, these are not possible, sort of a thing. Second thing is that Bhaskaran Raman's slide says that the branch history table has 2 columns. One is the branch address and the other is the taken, not taken, bit. But actually they do not contain the address in the branch history table. They don't need to, because they use the branch address to index into the table. Now, when you say I have 1024 entries in the branch history table, you only need 10 bits to address all the locations in the branch history table. Okay. So one method of doing that is use the last 10 bits of the branch address, for example. But because every instruction in MIPS is 4 bytes long, and so the last 2 bits will always be 0. So we do not take actually the last 10 bits, but leave the last 2 bits out because they'll always be 0. And take the 10 bits starting from the 3rd bit position and use that as the index into the branch history table. So then, the prediction will tell me whether it's taken or not. Now, obviously, multiple branches may have the same 10 bits, which means that all of them will be indexing into the branch history table. And therefore, the prediction is not for the branch you're looking at, maybe. It does not matter, because this is only a prediction. It doesn't mean it's always going to be true. If the prediction is found to be wrong, then, as normally done, the processor converts all the fetched instructions which are wrong into no ops and starts fetching the right instruction. So it's not like we are creating any trouble, but if our prediction is correct, then we are actually going to have no stops. That is the hope. Okay, or at least we'll reduce the number of stops. So that is the purpose of branch history prediction. Okay, let's look at the next slide and then maybe hopefully we'll understand what we are saying. So if this is the loop, okay, this loop basically calculates the sum of the first 10 numbers. How do you know that? Because when I say add R0, R0, R10, remember that register 0 contains only value 0. It never contains any other value. So this will mean that register R10 is set to 0. Okay. I am now adding 10 immediate value to R0 and storing it in R12, which means that R12 contains the value 12. Then I'm saying BQZ, which means 12, R12 is equal to 0. Okay. Then exit. Okay. Otherwise, what do? Add R10, R10, R12, right? So I'm starting at R12, 10, adding it to R10, which was initialized to 0, and storing the value in R10. Then I'm subtracting 1 from R12, and then I'm jumping back to the loop. Okay. So this is essentially the code instructions, which set of instructions which calculate the sum of the first 10 numbers, right? Okay, so how many, if you assume that we have a not taken prediction in the BHT, we start off with, we basically make the assumption that the branches are not taken. So the BHT is initialized with the value 0 in all the locations. How many mispredictions do we have for this loop? This is the question. Please work it out. Anyway, Bansi has said 5 minutes. I think the best thing we can do is leave the meeting. Okay. You work out. We'll join back in like 2-3 minutes. It's in my watch, it's 2:36. So we'll join by 4 more minutes. Okay, at 2:40. Work out how many mispredictions we'll have. Basically, when you say BQZ, R12, exit, that's a branch. So you're saying this branch will not be taken. So you will fetch add instruction. JMP loop, you'll assume it's not taken the first time. Now, how does BHT work? Whenever its prediction is wrong, whatever the actual action that has been taken, it updates the table. Okay, it updates the table. So when the first time JMP loop says not taken, if it is taken, then the value corresponding to the JMP is changed to 1, which means that the branch is taken. And basically that's what will happen. Okay. So actions overall will when we finish the loop. That is the question. Let us join for meeting.